So let's go a little bit of an overview of what we're going to be doing today. Our topic is 6.1, roots and radical expressions. We're going to move into 6.2 a little bit as well, but focus on 6.1. Our objective for today is to simplify, multiply, and divide radical expressions. We'll find that simplifying is the main thing we're going to be doing today, with multiplying and dividing is really just the first step of a problem that always leads to simplifying in the end. All right. We'll demonstrate this on the exit ticket, the end of class, the quiz in a couple weeks, and then the unit test at the very end. Right? It's a little bit of the overview. The vocab for today is, we'll be going over it in a second. It's all about radicals and indexes and everything. Then we have this we do practice right here. This is all about simplifying the first two examples. Then we go into multiplying right here. And then we have dividing. Then we have some you do problems for you to check to see what you know and what you don't know before we start on the exit ticket at the end. Do you have a question?
Okay.
All right. So we'll start with our vocab. Again, we're talking about radical expressions. So that means that we have that radical bar, which is a square root, cube root, all that type of stuff. There's a couple of things that we're going to go over first before we go into kind of the different things they're talking about. And that's about how we kind of define a radical. All right. A radical is defined by the kind of like whatever the solution for something would be. So a to the n is equal to b means that my nth root of b is my solution for a. Right? That's kind of how we define square roots. It's kind of a roundabout way of defining it because it's a weird symbol for us. Right? But really what this means is something that we've already talked about. Like with this, n is even. So what this says down here, just like we've talked about before, is if we had something like x squared equals 4, the solution to this equation right here, x would equal, just like this says right here, plus or minus the square root of 4, which is, just like we know, to be plus or minus 2. All right, and so it's saying that exact thing, is if n is even, if this number right here is even, and this number is positive, then our solution will be like this, plus or minus the square root. This one is also something we've gone over before, something like x squared equals -9, where we have, again, even number, we've already talked about before, and then a negative, and we end up with imaginary roots of x equals plus or minus the square root of -9, which is equal to plus or minus 3i. So when we get those imaginary roots, whenever we have that negative, right? So that's how we get our solutions for these two, and that's for the even cases. If it's even and the other number is positive on the other side, like this 4, we get the plus or minus just like we're used to with the square root. If it's even and it's negative, then we get our imaginary roots. Now we have one more thing that we're going to talk about today. It's kind of the new part, right? Which is the odd part. So if we had something like, let's say something like x cubed equals, let's say, 8, this will say, just like we did before with taking the square root of it, x equals the cube root, where we have a 3 right there. What we're going to call this our index, which is equal to 2. All right. And notice how it just has one solution right here, just the 2 right here. So it'll only have one real solution. There'll be two other solutions, but they will be imaginary numbers. So we won't actually have to do anything. Again, this is how we do it. X equals 2. Taking the cube root of it, taking the opposite of this. All right. Now, up above it, depended on whether it was positive or negative, it turns out with x cubes, it actually doesn't matter because x cubed to the -8th, the cube root of -8 is actually just a -2. Because -2 times -2 times -2 gives me that -8. I don't need any imaginary numbers. So you can see whether it's positive or negative, it's still a real number in the end. So we don't have that same problem that we did up above with the square root being that. Right. Let's pause for a second. Does anybody have any questions on what we've gone over so far for either even and positive, even and negative, or odd? Right. Does anybody have any questions on any of these three sections that we went over? Anybody completely lost and want me to go back over anything? Any of that type of stuff? Let me know. No? All right. So someone said that they don't quite understand the odd. That's fine. It's the new part, so it kind of makes sense. We'll learn a little bit more about it later on in the section when we're talking more about solving. Let's go over it again. The trick is that I do the opposite of whatever power is here. All right. So when we're square rooting up here, there's actually an invisible 2 that we don't see right here. All right. So that's why we square root. There's that invisible 2 actually right up here. Invisible 2. Down here, we have an actual 3 that we show. And so the number that multiplies 2 times 2 times 2 equals 8. So that's how we got that 2. All right. And then -2 times -2 times -2 times -2 times -2 gives us 4 times -2, which is -8. All right. So that's how we get that -8 right there. All right. So that's kind of the process we're going through. Don't worry too much about the actual math involved. Just make sure you understand that if x cubed equals some number, we're going to take the cube root of it to get our answer. And even further, think about the fact that it'll only give us one real solution. All right, we'll only ever get one solution out here. Unlike up here, we always ended up with 2 solutions. All right. So 1 real solution, 2 real solutions, no real solutions. All imaginary. That's kind of what we got to think about. That's the focus of this kind of thinking right here. Right? None, 2, 1. Right? It's just talking about the fact that it's odd versus even. Odds will give you one solution no matter what. Right? Does that answer your question, or do you want me to go more in depth or anything? Sometimes, you know, a teacher can start talking, think they're answering their question, and not really give you a good answer. So let me know. I think that it'll make more sense as we go as well. So even if you don't feel like you fully understand it now, you'll probably get it by the end. All right, so let's move on a little bit to what's down below. Right here, this index, radical, and radicand. My index is the number out front. All right. It's that number on top of that little pedestal. The actual bar is called my radical. Okay. And then the part inside is called my radicand. Those are my 3 main things. We have, just like we've seen before, some very basic ones like the square root, which is our basic one where we have the invisible 2 out front. Then we have our cube root, which is our next kind of regular one we see. Then we keep going up from there. Fourth root, and then fifth root. All right, and just keep going up from there. Cube root, fourth root, and then square root. Square root. Right, square is not easy to do with your mouse. All right, and then fifth root. So that's how we write those out. That's what they mean. There's that invisible 2. Don't forget about that with our square roots. I think that that is what most people make a mistake on. One thing that we can also do with these is that this radical and everything connects in a way with our exponents. All right, so let's say that we had something like the square root of x to the third power. All right, I can change this square root, this invisible 2 right here, into an exponent by putting it as a fraction. So I can go x to the 3/2 power. So that's another way we can write our exponents, our radicals. All right, we can put it in exponent form is what it's called, with 3/2. Same thing as if I had something like, let's change it up and put 3, the cube root of, let's say, y to the 5th. That's going to be equal to y to the 5/3. All right, so all I do is leave everything else the same, but I divide my exponent by whatever my index is. That's how I change from radical form to exponent form. Right? Sometimes it's easier to do this and then simplify a little bit. It makes it a little bit nicer to do some math, but it's not really necessary. You can always just keep it in this form and do the math that way. All right? I'm just showing you that just in case you like that method more. We'll see kind of where it can help. Are there any questions on any part of the radical, any of the names over here, or how to go from radical form to exponent form? Anybody need me to repeat anything? Go back over it. Circle back around. All those buzzwords. And I'll give you about another 5 seconds to answer. If not, we're going to move on. 4, 3, 2, time. All right, we're going to move on to some actual problems. See if we can kind of make more sense of this. All right. So first thing we're going to do is kind of decide what a cube root is. All right, we're going to talk about that. So like with this first one, I'm going to rewrite this as a cube. So 8 is equal to 2 cubed. If you're ever wondering what something the cube root of is, you can use a calculator. If I come over here, let's calculate. My cube root button is, I get it from here. This would be a great one to be able to use your thing right here. And so you can go something like 8 to the power of 1/3. Oops. Here. This is not a good calculator. So a better calculator, this is much better. There we go, cube root. And so we go 8 to the power of, and then we put in our 3, and we put equals, and it'll give us that 2 that we want. All right, so you can do that with any number you want. Some of them are nice, some of them are not. All right, and I'll show you how to simplify them as well in a little bit. There'll usually be an y to the x by. Same thing over here. Negative 1,000 can be rewritten as negative 10 to the third power. Notice that the negative is on the inside of my parentheses. That's very important when you're writing these out. You're trying to do this, is that this whole thing is being cubed. Right? So negative 10 is the cube root of negative 1,000. Right? Same thing for 1 over 27. Some part down here. The 27 can be rewritten as 3 cubed. So 1/3 is the cube root of 1 over 27. Because again, as long as I can rewrite it as a cube, that's going to be my cube root. All right. I don't think that really, does too much for actually understanding, like actually doing problems, but it's a good thing to think about, right? So that's kind of how we actually define a cube root. We define a cube root by the number cubed equals that number. So the cube root of 8 is 2 because 2 cubed is 8. And that backwards thinking that we have. All right. Don't worry if that's a little confusing. We're going to move on to here, where some actual problems that we'll see. And the trick to these always is to get this number out front to be my exponent for all of these. So I have an invisible 2 out front. And so I want to make this 16 have a power of 2. I want to make this x to the 8th have a power of 2. To do that, I change that 16 into 4 squared. And I change that x to the 8th to be x to the 4th squared. All right. Once I have that, I know that the square roots and the squares are going to cancel out. And so both of this and this are all canceling out. And so I end up with 4 x to the 4th left over. Because all of the square roots and the squares canceled out. But again, I want to talk about the fact that to do this, we specifically made it so that we had the same thing out front. The index matched my powers. So this invisible 2, oops, that's a bad 2. Invisible 2 match that exponent and match that exponent. Right? Another way you could do this if you don't really like this method, is I also can think about it as, and change it into fraction form. So the square root of x to the 8th can be rewritten as x to the 8 over 2, which is equal to x to the 4th. All right, so that's using my exponent form to solve this and simplify. All right, that's another way you could do this. Another way you could do this is to make them all squareds. So instead of trying to make it x to the 4th squared, you could rewrite x to the 8th as all x squareds. So x squared times x squared times x squared times x squared. 2 plus 2 plus 2 plus 2 gives me 8. I square root all of those, square root all of those, and I get x times x times x times x, which is equal to x to the 4th. Right? Those are all options on how you can factor these. And again, that's an invisible 2 right there that cancels out with these ones right here. All right? The square root right here canceled out with that square right there. Right? Same thing up here. This 2 right here canceled out with these 2's up top. Canceled out. All right. Remember, these are all 3 ways that you can simplify this. Are there any questions on any of the different methods I used? Or anybody confused overall, want me to go back over the problem? Anything at all? right, then let's move on to our second one. B right over here. We're going to follow a very similar path. Just like before, we tried to make it so that this 2 out here, this invisible 2, match my exponents up here. I'm going to do the same thing over here. I want this 3 right here to match my exponents up here. Right? Actually, undo. Let's put a text box. It's much easier to read. Set the exponents. That's what I got to do for these problems. So to do that, I'm going to get back out my draw pen. I'm going to undo this part right here. I'm going to rewrite that 54 as 27 times 2. Reason I rewrote it as 27 times 2 is because of the fact that I use my factor tree. Just like we did before when we were talking about simplifying square roots, 27 can be rewritten as, 54 can be rewritten as 9 times 6. 9 can be rewritten as 3 times 3. And 6 can be rewritten as 3 times 2. And with these factor trees, I'm always trying to find whatever powers out here connects. So in this case, I had 3 3s. I want 3 of them. So I got all 3 3s, and then I have a 2 left over. 3 times 3 times 3 gave me 27, 2 left over. Okay. So then I can rewrite this as, it's right here. Select this right here so we can see it. Part of it didn't come with me, which is annoying, but it's not a big deal. So again, I rewrote that 27 as 3 cubed. The 2 can't be rewritten as a cube, so I leave it as a 2. And then I broke up this x to the 5th as an x to the 3rd times x squared. The reason I do that again is just like I said before, I want to get the exponents to match. So now this 3 right here, and this 3 and this 3 right here, all match this exponent out here. Right? All match this exponent out here. That's always what I'm trying to do. Get as many things to match whatever index I have out front. So since they match, I can cancel those out. So the cube root of 3 cubed is just equal to 3. And the cube root of x cubed is equal to x. All right, so we end up with, this is our final answer. 3x on the outside, because both of those can cancel out with the cube, with a 2 and an x squared left over on the inside. Are there any questions on how we did that problem? Anything anybody's confused about? Anything anybody wants me to go back over, re-talk about, anything along those lines? Anybody needs me to reiterate anything? It's a great thing to notice. So my exponent was canceled for these two and this one, but it was not canceled for this one and this one. These two did not have a cube in it. All right, so I couldn't cancel those ones out, so they stay inside. This one went away over here because we canceled out everything on the inside. Both this one and this one both canceled. In this case over here, we didn't cancel out the 2, and we didn't cancel out the x squared term. All right, those were left over. But the 3 and the x both took outside, all right, because those did cancel out. This one did cancel out because we can cancel out these two. We can't cancel out these two. All right. So someone wants me to re-go over B, so I'm going to re-talk about it again. So I'm going to clear off my screen. We're going to go right back over B. Full process. The first step again with this problem for B is that I need to get it into cubes. So I need to make all of these exponents match this little index right here. All right, I need it to match. To do that, I need to factor 54 into some cubes. Right? I like to think of it as two separate things. So 54 first, and then the x to the fifth. With the 54, just like I did before with my factor tree, I break it down into two things that multiply together to be 9 and 6, let's say. Factor those two, I get 3 and 3, and 3 and 2. And then since I want 3 of them, I circle together any 3 they have in common. 3 times 3 times 3 gives me 27. So that's where that came from. Then I have my 2 left over that don't connect with anything. So that's going to be left over on the inside. Factor it a little bit more, I get my 3 cubed and my 2. And so that's how I kind of do the regular numbers. Then I go back and do my x's. So I have an x to the 5th right here. And I want it to be a 3 power. So I want it to match. To do that, I make it a 3 and a 2. Because 3 plus 2 gives me that 5. Again, I want it to be a 3 so that I can get it to match this number out front. Right? Because once it matches, then I can simplify it. If it doesn't match, then I can't simplify it. Right? Rewrite the 27 as 3 cubed. Both this one and this one can be simplified because they both have a power of cubed. While these two can't be simplified, the 2 and the x squared can't be because they don't have a power of cubed. So they stay inside, and these two go on the outside. Are there any questions left over on that process? Anybody confused about that? Anybody need me to re-go over anything else? Re-talk about it? Confused on how I did the factor tree for 54? Confused on how I got x cubed times x squared and how that matches up with x to the 5th? Any of those type of things? I will say, being able to simplify is the main portion of today. It's going to be very hard to do this rest of this class, this period. You can't simplify. Does anybody have any more questions on this process? Right, let's do this instead. Make sure that everybody's paying attention still and still kind of there. Put in the chat that you are ready to move on if you're ready to move on, and then put in your chat not ready or whatever you need me to go over in the chat instead. So let's repeat that, make it a little more obvious. If you're ready to move on, put ready to move on in the chat or whatever, something like that. If you're not ready to move on, tell me that as well. And then probably something like why you're not ready to move on. And I'm getting a couple responses. There we go. I'm gonna call that good. Seems to be that everybody. So we'll see some more examples down in the next problem. So let's move down into those and we'll see some more examples of how to simplify. So let's do this. Because again, we're going to be simplifying all of these. And so we'll do that same process. We're just adding one little step to the beginning. All right. So we'll go over how to simplify and everything again. Get you some more practice. All right, first things first though, let's talk about product of radical expressions. When we talk about products, as long as they have the same index, we can combine them into one fraction bar. Right? So since they both have the same n out front, same index, I can combine them into one radical. I repeat, they must have the same index. Right? So like this A right here, since this 3 and this 2 don't match, since they aren't the same index, we can't multiply them. Right? They do not multiply together. So then we were done with this problem. This would be my answer in simplest form. Then we have problems like this. Since they do have the same power, we multiply them together. Right? And we get -4 times 2. -4 times 2 is -8. Now we actually saw this above with the cube root of -8. We can rewrite that as the cube root of -2 cubed. So now that the exponents match in both of these, now that this cube root and this cube match, we can cancel those out, and we just end up with -2 in the end. And so that's a little bit easier of a problem to kind of see with that process. Multiply, change it into the matching term out front, simplify. So that's kind of what we do in these problems. I'm going to do that same thing for this one right here. This one's a little bit more like the problems we've done before. Scroll down a little bit so we have some more room. First step again, since they have the same index, the same invisible 2 out front, we multiply them together. We get this right here. 720, x to the 4th, y to the 5th. All right, let's start with that. Once we have them multiplied together, it's the same thing we did above. So let's go over it. First thing we need to do in these problems is I need to see what type of index I'm dealing with. So I have that invisible 2, which means I need everything to be a squared power, right? So I need this 720 to somehow be a square. I need this x to the 4th to somehow be a square. I need this y to the 5th to somehow be a square. And so that's what I'm going to try and do. So let's do a little bit of that math. First, I need to factor the 720. Let's do some pretty easy ones. 72 times 10. 72 is equal to what? 36 times 2. 10 is equal to 2 times 5. And 36 is equal to 6 times 6. So now that I have some things that are matching, I can box these together. I can box these together. Again, the reason I only need a pair in this case is because of the fact that we have a 2 out front here. Right? So we only need pairs. 6s, 2s, 5s left over by itself. All right. So this is what I end up with. 36 from the 6s, 2 times 2 with the 4s, and the 5s left over. Right? So that's for my regular numbers. Now with the other ones, the x to the 4th and the y to the 5th, I need to change those into squares as well. So what I first do is I change that x to the 4th, just like we did before, into an x squared squared, right? Because now it's a power of 2 like we wanted. Then we change this y to the 4th and this y to the 5th into a y to the 4th times y. The reason I chose y to the 4th is because now this is an even power, and so it goes into a square. It's a nice even power, that y left over. right? Now it's just a little bit of simplifying. Square root what I can square root, leave what I can't square root. So the square root of 36 is 6. The square root of 4 is 2. The square root of x squared is x squared. The square root of y to the 4th is y squared. And then what I'm left over with are the two things that couldn't be square rooted, this 5 and this y. Right? Everything else was square rooted, so it went out to the outside. It's only two of the things that stayed inside. Then a little bit more simplifying, you end up with this as your answer. 6 times 2 gives you 12. So that's the process we're going to do every time. These multiply, I multiply them together. I factor using that invisible number out front. I want to make sure all of those powers match. So I made it a same power here. I made a number that I can square here and here. Same thing over here, the y to the 4th. Okay. Are there any questions on that process? Anybody need me to go back over any specific thing? Any part that anybody's confused about? Any little piece along the way that anybody's having problems with? So I got 36 times 4 times 5 by using my factor tree. I broke 720 into 72 times 10. Broke 72 into 36 times 2. And then again 36 times 6 times 6. And then 10 became 2 times 5. And I put together anything that they have matching. The 6 and the 6 are matching pairs. So I put those together to get 36. The 2 times 2 is a matching pair to make 4. Then I had 5 left over. So that's how I got those numbers. Does that make sense? Or do you want me to explain more about my factor tree? I will say most people last class were able to do the factor tree part. Their problem was this part right here. Right, so make sure that you understand how to do this part with this y to the 5th. I always want to make that exponent be divisible by this number out here. All right, so I took away 1y because y to the 4th is now divisible by 2. Right, goes into 2. Same thing that we did above, where we went with the x squared and the x cubed to make a match. Let's move on to our last section because we're running up on the end of class. I don't want to give you all enough time to finish up. We're going to talk about quotients now. Same thing as what we did before. Same process. What we have to do is we have to divide them. If they have the same index out front, then we can put them into one fraction. If they don't have the same index, we can't do that. All right, just like we did before. Since these two have the same index, we combine them into one fraction. We get something like this. Then we do some simplifying. Combine them 1. 18 divided by 2 is 9. Just like we did earlier today, we subtract these two. All right, this gives me 9. This gives me nothing, 1 left over. Cancel this out, subtract 3 from here. It's not working. And I end up with this right here. Oops, give the full answer. Oh well. 9x to the 9x squared, square rooted. The square root of 9 is 3. The square root of x squared is x. So my final answer is 3x. Now there's something that the book does with their answers. It's a little different than what I usually do with my answers. What the book does that I don't do is that whenever there's an odd power, they include absolute value bars. Right? The reason for that is because of the fact that they have not introduced imaginary numbers in their lessons yet. Right? We are currently in chapter 6. They don't include imaginary numbers until chapter 8. We've actually already gone over chapter 8. We skipped ahead to that and then moved back to this chapter. And so because of this, the book thinks that we haven't gone over that when we actually have. And so they have to have a couple weird rules that we don't need because we've already gone over. So the absolute value bars right there are extra. Okay, so our answer will be equals 3x. The book's answer will be this right here. Now it only happens with odd power. So there's that invisible 1 up top. So because we have that invisible 1, we have an odd power. So they put absolute values around it. If it were an even power, then we don't even need to do that. And again, that's specifically because of the fact that they don't have imaginary numbers yet, and we already do. It makes it a little bit tricky for some of the problems. For the test, you won't have to do the absolute value part. You'll just have to do this part. But some of the homework, since it doesn't know that you know know imaginary numbers, they'll make you do that. Right? Are there any questions about that process? Any questions about the absolute value bars? Any questions about how we simplify those fractions? Anything along those lines before we move on to number 2? All right, let's go to the last one. If you come up with a question on number 1, we can go back to it. So first thing, make it into one fraction bar since they have the same index. Then simplify. 162 divided by 3 is 54. Y squared divided by y cubed. And y squared divided by y to the 5th gives me y cubed. Same process as we did before. Divide by 3. I get 1 and 54. Cancel this one out, subtract 2 up here. 5 minus 2 gives me that 3. All right. Then it's the same process we did before with factoring a little bit more. Rewrite them as cubed. We've actually already done 54 from above, so I just took my factored form from above, put it here. Y cubed was already a cube, so that's nice. So we end up with 3 and a y on the outside, and the 2 left over on the inside. That's my final answer. All right. Are there any questions on this problem? Anybody confused on any part of this, knowing that you're about to do the you do section and the exit ticket on your own? Any questions? All right then. So it doesn't seem to be any questions. You all can start on the you do problems and then start on the exit ticket afterwards. Let me know if you have any questions. I'm here to help at any point, and good luck.